you ate this lunch, you know you'd be getting energy from the food. But you'd also be getting a different kind of energy. Something on that table is sending out invisible energy detected by the probe. The radiation seems to be coming mostly from the bowl with the fruit in it. Is it coming from the fruit or the bowl? The energy is coming from the bowl. Put it to one side for the moment. Even with the bowl gone, you're still exposed to this unseen radiation. Every day of your life, no matter who you are, where you go, or what you do, you're bombarded by it. It's a part of the natural environment and has been since the beginning of time. You're going to investigate this invisible, everyday radioactivity. These three discs are the ABCs of the radioactivity in your daily life. The different radiations they give off are known by the first three letters of the Greek alphabet. Alpha is the radiation coming from polonium-210, a radioactive element discovered by Madame Curie in 1898. Atoms of the polonium-210 are spontaneously giving off alpha particles, which are entering the probe and triggering pulses of electricity inside. The current is amplified by the instrument. You can see the flow of current on the meter calibrated in counts per minute. Each burst of current makes a clicking sound come from the speaker. You've probably heard the instrument called a Geiger counter. Put a piece of paper between the polonium-210 and the probe. The current drops, showing the paper has blocked the alpha particles. Nuclear researchers have found that alpha radiation is made up of subatomic particles that can be stopped by such things as a sheet of paper, your skin, and other relatively thin materials, such as air. Beta, the second Greek letter, is the name given to the radiation coming from strontium-90, an element chemically similar to calcium. The betas are also picked up by the probe and register a little less than 200 counts per minute on the meter. The paper that stopped the alphas has little effect on the betas. They go right through it. Research has shown that betas are also subatomic particles, but have more penetrating power than alphas. Now put a 3/4 inch thick piece of wood in the path of the betas. The wood absorbs most of the betas. Beta particles are stopped by such barriers as wood, thin sheets of metal, walls, and many other materials. And finally, the third kind of radiation. You may have heard of cobalt-60 in connection with cancer treatment. The atoms of cobalt-60 give off beta particles and a different kind of radiation called gamma, the third letter of the Greek alphabet. The combination of betas and gammas results in 300 to 400 counts per minute. Bring in the same paper. The radiation from cobalt-60 goes right through it. Next, the wood. The cobalt-60 betas are absorbed by it, just as the betas from strontium-90 were. Now you're measuring only gamma radiation. This is a 1-inch thick barrier of lead sheets. Most of the gammas are absorbed by the lead, as the meter shows. Almost all of the radioactivity in your everyday life is made up of these three kinds of radiation. Alpha particles, which are stopped rather easily, beta particles, which have moderate penetrating power, and the highly penetrating gammas. Which kind of radiation, alpha, beta, or gamma, is coming from the bowl? The sound tells you that the bowl is highly radioactive. Alphas, betas, or gammas, or a combination of them, are entering the probe at the rate of about 425 counts per minute. To find out what makes the bowl so hot, fasten the probe to the case. Next, put it on a block so that the probe is held at a fixed distance above the bowl. The alphas will be stopped by the paper. Because the count per minute drops slightly, you can suspect that some alphas are shooting out from the bowl. Now for the wooden beta barrier. Obviously, most of the bowl radiation is made up of betas. The remaining radiation is probably gamma. The lead blocks almost all the rest of the radiation, indicating it is gamma rays. What material in the bowl is giving off all this radiation? The alphas could be coming from polonium-210 in the bowl. Strontium-90 could be the source of the betas. Both betas and gammas could be supplied by cobalt-60. But other radioactive sources also give off alphas, betas, and gammas. Uranium emits all three. So does radium. Finding out what kind of radiation is coming from the bowl or any other radioactive source is only the first step in identifying the actual source of radiation. To pinpoint the specific radioactive material in the bowl, you'll need an instrument known as a scintillation counter connected to a multi-channel analyzer. It may look complicated, but the principle on which it works is easy to understand. Its probe detects only gamma radiation. At the bottom is a thin metal shield which gammas can easily penetrate. Inside is a crystal that reacts in a peculiar way when it absorbs gammas. This is not the crystal. It's a circle of tissue paper that represents the crystal. The projector will be the source of gammas. The light represents the gamma radiation. When gammas are absorbed by the crystal, some of the energy is converted to light. Not a steady beam like this, but short flashes of light, more like this. Scintillation means flashing in Latin. The light produced is picked up by a special photocell that converts some of the light energy to an electric current. In this model, the light sensing cell is similar to that in a photographic exposure meter. In the actual scintillation counter, it's a photomultiplier. The current generated by the photocell makes the needle of the meter move. Notice there's a pulse of current for every flash of light produced by the gammas. If you turn up the brightness of the projector to represent gammas of higher energy, the flashes of light they produce are brighter. The higher energy generates a stronger current. Each pulse of current is in direct proportion to the energy of each gamma. Now let each burst of current be represented by one of the red balls in the trough. Inside the scintillation counter is a memory. That's what those channels on the lower right are supposed to be. The value of a given pulse of current is stored in the appropriate channel. The energy of each gamma determines where the information is filed. As more and more gamma energies are measured, the data in the memory begins to show a pattern. Scanning the channels now shows that most of the gamma energies had a value of 8 in this model. Of course, there are no balls inside a real scintillation counter. It's a highly sophisticated electronic device for detecting, measuring, storing, and displaying gamma energy patterns. Now that you know how it operates, you're ready to use it to measure the energy of the gammas from cobalt-60. The instrument is all set. The gammas are penetrating the crystal, generating flashes of light that are picked up by the photomultiplier. Each burst of current is being measured and then displayed as a tiny dot of light on that round screen. The dots that represent the gammas of the same energy are added together like the balls in the slots. Gradually, the pattern formed by the cobalt-60 gammas develops. Here's a photographic record of the cobalt-60 gamma energies. Later, you will compare it to the gammas given off by the bowl. What do you suppose the curve for uranium will look like? You'll soon see for yourself. Uranium gammas are creating flashes of light, which are changed to bursts of electric current that will eventually show up on the screen. The gamma radiation from uranium produced this pattern. Here's the photograph of uranium gamma energies. Note how different the pattern is from that of cobalt-60. Now to check the gamma radiation from radium. This is the photograph of the radium gamma energies. Compare it to the others. Remove the radium source and put the bowl under the probe of the scintillation counter. If you suspect that it contains cobalt-60, uranium, or radium, you're right, it does. But which one? The measurement of the gamma energies coming from the bowl will give you the answer. As soon as the bowl gammas have been measured and stored, you can compare them to the patterns of the gamma energies from cobalt-60, uranium, and radium. Here's the photograph of the bowl gammas. Is it similar to cobalt-60? Uranium? Or radium? The pattern of the gamma energies from the bowl matches those of uranium, so the bowl contains radioactive uranium. The orange glaze on the surface of the bowl contains uranium ore, which was once mined for its color. The ore contains radioactive uranium-238 in it. Today, dishes like this are no longer made in the United States because the radiation from the uranium was found to be potentially dangerous. Uranium is now mined for use as fuel in nuclear reactors that power ships and submarines, as well as generating plants that can produce enough electricity for millions of people. For many years, the dials of watches and clocks that glow in the dark like this were coated with radium. Radioactive tritium is now used instead of radium. Radium has proved to be an effective treatment for certain types of diseases. Other ordinary things are also radioactive, This is a mantle for a gasoline lantern. It's slightly radioactive because it's coated with thorium-232. The burning gasoline heats the thorium, producing a brilliant light. Scientists have discovered radioactive elements in many more everyday objects besides uranium bowls, radium dial clocks, and thorium mantles. They found, for example, that you're exposed to a very small amount of low-energy radiation every time you watch television. Not very much, but a measurable amount. The radiation you receive when you watch 1 hour of color television each day in the year can be considered a sort of unit of everyday exposure. 365 hours of watching color television will then have a value of 1. If you live in a wooden house, you receive about 17 TV units of radiation each year from natural radioactive materials in the wood. Bricks are even more radioactive. In a brick house, you get approximately 36 TV units in a year. Everywhere you go, you're bombarded by what is called cosmic radiation. Scientists have identified it as radiation coming from the sun and outer space. Some of it can penetrate the atmosphere, buildings, and people. At this very moment, some of it is going right through you. If you live at sea level, the cosmic radiation you get in a year is about 20 times what you receive from watching 365 hours of color television. Every 200 feet above sea level increases your cosmic radiation by about 1 unit each year. A 10-day vacation high in the mountains exposes you to cosmic radiation of 1 more unit. The ground you walk on is also a source of radiation, adding 7 1/2 TV units a year. Minute amounts of these radioactive elements are taken up and stored by plants. Cereals, Brazil nuts, and tea are some of the plant products that are relatively high in these elements. Animals eat the plants and concentrate the radioactive elements in various parts of their bodies. You're exposed to some of this plant and animal radioactivity in the food you eat, and more in the water you drink. On the average, food and water add 12 1/2 TV units of radiation a year, mostly beta and gamma. You and the people around you give off measurable amounts of beta and gamma radiation. Even the air you breathe is slightly radioactive, giving off alphas, betas, and gammas that add 2 1/2 TV units per year to your total. Nuclear power plants are a source of radiation to people who live near them. Assume you spend 24 hours every day in the year at an average of 5 miles from such a power plant. The radiation you'd receive would be equal to about 1/40th of a TV unit, about 8 days' worth. A single dental x-ray exposes you to 10 TV units. A chest x-ray averages about 100. Medical x-rays expose you to more radiation than any other source. Not including x-rays, the total amount of radiation you get in a year averages about 100 units, as much as watching color television for 100 years. Even without the uranium bowl, the food you eat, the water you drink, and the air you breathe expose you to radioactive elements. Radiation is emitted by almost everything around you. Now you know that no matter who you are, where you go, or what you do, you are constantly bombarded by the alpha, beta, and gamma radiation that's a natural part of your environment. Your everyday radioactivity.
I'm Don Herbert, although some of you may know me better as Mr. Wizard. For years, I've tried to make science and technology interesting and understandable through books, kits, motion pictures, and, of course, television. Right now, I'm in my combination workshop and laboratory in Camarillo, California. Recently, I had the opportunity of looking into the questions people are asking about the use of nuclear energy for generating electricity. Such nuclear power questions as, can a nuclear power plant blow up like a bomb? Can it survive an earthquake? How much radioactivity does it release to the environment? What kind of safeguards are there in case of a major accident? Is the long-term storage of nuclear waste a problem? What you are about to see is a filmed report of those nuclear power questions and answers. We begin, of course, with question number 1. Can a nuclear power plant blow up like a bomb? Well, a nuclear power plant, in many ways, is like any other power plant, including this one. It may look like something out of Mr. Wizard, but it's a real power plant and will generate electricity. When I move the gas flame under the flask, the water inside will be heated to boiling. Steam under pressure will flow through the tube and strike the vanes of the turbine, making it spin. The turbine is connected by a shaft to many turns of wire wound together. As the wires spin within the magnetic field of the magnet, an electric current will flow through the wires to the meter. Well, let's see if it really works. The water's already hot, so it shouldn't take too long. As you can see, the meter shows a current of almost 0.008 of an amp. The power plant that supplies you with electricity works on the same principle, but generates several million times as much current. Now, the 4 important parts of your power plant and mine are a generator, a turbine, a supply of steam under pressure from water in a boiler, and a source of heat.
This Mr. Wizard model of a nuclear power plant begins with the same components: a generator and a turbine. Below them is a cooler, where the steam coming from the turbine is changed to water and piped back to the boiler to be used over again. The heat to boil the water comes from a unit known as a heat exchanger, because that describes what goes on inside. The water is changed to steam on one side by heat flowing through the other side. There's no direct connection between the two systems, so only the heat is exchanged from one side to the other. In a nuclear power plant, the heat is supplied to the heat exchanger by water circulating through the reactor. In the model, bits of rubber make the flow within the reactor visible. The nuclear reaction going on in the fuel rods produces the heat. The heat output is regulated by control rods placed between the fuel rods. To increase the heat output, the control rods are raised. More of the fuel rods are exposed to each other, so the nuclear reaction produces more heat. To decrease the heat output, the control rods are lowered, and the nuclear reaction produces less heat. Now, question number 1. Can a nuclear power plant blow up like a bomb? Remember, a large part of a nuclear power plant is much the same as any other power plant: generator, turbine, cooler, and boiler. The big difference is in the source of heat. Any unusual increase in temperature or pressure triggers the control rods to drop, stopping the nuclear reaction.
That's only part of the answer. The other and more important part is the amount of uranium in nuclear fuel. Pretend these balls are atoms of uranium. To make a bomb, you need 2 quantities of almost pure uranium, and then bring them together with tremendous force. In a real bomb, this is done with explosives. Almost instantaneously, a chain reaction results in the explosion of the bomb. Now, the heat in a nuclear power plant is supplied by less than 4 atoms of pure uranium fuel for every 96 atoms of other material. The uranium fuel is in effect diluted by the other atoms. In addition, the other 96 atoms which are not present in a bomb have the property of shutting off the nuclear reaction if the temperature starts going up. So the answer to question number 1 is no. A nuclear power plant can't blow up like a bomb. Now, question 2. Can a nuclear power plant survive an earthquake? There was a fairly large earthquake in the San Fernando Valley in 1971. Could damage like that happen to a nuclear power plant? The first man we talked to was Gale Hunt, one of the geologists who studied the possible sites for the first commercial nuclear power plant in California.
Well, we studied the geologic maps made by geologists over the years to find areas where there are no active faults and where earthquakes do not occur. We gradually zero in on 3 candidate sites after looking at possibly 20 or more. Then we began a feasibility examination of the potential sites, not necessarily in detail, but to determine which is the most suitable. We then recommend the best of the 3 be thoroughly studied, and that's how the site of San Onofre was selected. As you know, it is located on the coast, and we see good exposures of the geology along the beach for miles both up and down the coast. Looking at these sea cliffs, we can see a picture going back to millions of years. We see evidence that the area is very stable. Rocks aren't tilted, they're not folded, and they're not cut by faulting. The only fault of any interest was the Christianitas fault that runs in a northwestern direction and cuts the coastline about a mile south of the site. What you see in the cliff face, Don, is a fault that cuts rocks that were laid down on the seafloor as much as 10 million years ago. The fault, as you can see up here, is truncated by that horizontal line of cobbles, which forms a geologic boundary that we would call an unconformity. Above the unconformity is about 40 feet in thickness of sandstones and cobbles, which we have dated as being greater than 100,000 years in age. The fault, of course, does not cut those cobbles and boulders. The AEC criteria stipulates that a fault be considered active if it's moved in the last 35,000 years. We know that this fault has not moved in the last 100,000 years, and therefore the possibility of it moving in the future are just extremely low. We meet the AEC guidelines and specifications, and we believe that the fault is certainly inactive. But to be positive, we dug down at 30 to 40 feet depth below the ground surface at various distances from the fault to look for vertical or horizontal offsets of the soil and rocks measured in inches, and we found none. Geologic consultants made independent surveys of the site, they reviewed our work, and they agreed with all of our findings.
How does this kind of survey compare with those done for, say, a large office or an apartment building?
Well, there's really no comparison. Let me put it in terms of dollars. To build a large 30-story office building, one might spend $20,000 or $30,000 for this type of exploration. For a nuclear power plant, the surveys are much more detailed and extensive, costing on the order of $1 million or more. We carefully study not only the site area, but every fault within 100 miles that might cause motion at the site, and we calculate what that movement might be.
The San Andreas Fault is nearby, isn't it?
The San Andreas Fault is located about 60 miles over in this direction. If a giant earthquake were to occur on the San Andreas Fault, one larger than ever recorded, we could expect ground motion at San Onofre to reach a certain degree level of intensity. We doubled then the calculated accelerations from the San Andreas Fault and then added a safety factor. And we finally provided the structural engineers with a considerable margin of safety to design to.
How about the plant itself? Was there any special consideration given to the effects of an earthquake?
Well, why don't you talk to Asa Hodgian of Bechtel for that? Bechtel designed the plant, and he was responsible for the seismic part of it.
I'll look him up, Gail. Thanks very much.
Okay.
Asa Hodgins studied earthquake engineering at the California Institute of Technology and has been specializing in nuclear power plant design for the last 9 years.
We don't treat nuclear power plants as normal structures at all. We take a completely different attitude.
In what way?
Well, if a large magnitude earthquake occurred, an ordinary building like this one may deform to a point where it might not be any more useful. But hopefully, and that is the intent of all building codes, it will not collapse so that life and limb will be saved. However, a nuclear power plant will go through a major earthquake without showing any kind of serious distress.
No damage at all?
Well, we actually design for 2 kinds of earthquakes. One is called the operating basis earthquake. The plant is designed to be able to continue to operate normally after such an earthquake on the condition, of course, that non-safety related items continue to function. Then there's the safe shutdown earthquake, which is more severe and not really expected to occur. We designed the plant so that should it occur, some of the components that are not safety related, like the turbines, may be damaged, but not the safety related components like the reactor. The reactor and all the associated equipment that is safety related would remain undamaged, so that